welcome back. So we were discussing about how to compute the space complexity and the time complexity during the last few sessions. Now in this session, let us discuss about the asymptotic notations. Hope you know the meaning of asymptotic. Asymptotic means unpredicted behavior. So say if you consider a person, or say consider a student, his behavior inside the class will be different from his behavior outside the class but within the campus. But if he goes outside the campus, his behavior will be different. At home, it will be entirely different. Similarly, the behavior of the algorithms for different values of inputs may vary. So the behavior of the algorithm may vary depending upon the instance characteristics. So in order to predict the time complexity, it's not easy to predict the time complexity as an accurate value. We just say it's better than, so we can approximate the time complexity as say 2n plus 2 or 3n plus 3, etc. So that's why the concept of asymptotic notations is introduced. So now there are three types of step count: best case step count, worst case step count, average case step count. It will be more clear if you listen to this example. Say consider the binary search algorithm. If the element to be searched is exactly at the middle of the given array, the task is easy. Immediately we get the answer. It's the middle element. So the time complexity will be just 1 or 0. But if the search element is either first element or the last element, the time complexity increases. So depending upon the position of the search element, the time complexity varies. That is the unpredicted behavior of an algorithm. So we just categorize it as best case step count, worst case step count, and average case step count. So what is best case step count? Best case step count is the minimum number of steps that can be executed for the given parameters. Worst case step count, the maximum number of steps that can be executed for the given parameters. Average case step count, average number of steps that can be executed for the given parameters. So we specify the range. The best case would be the minimum best case step count. In the worst case, then that is the maximum value. The average number of steps that can be executed for the given parameters. So we define 3 types of asymptotic notations. Big O. Then before defining the notations, asymptotic notations, let us see what is the need for calculating the time complexity. So this question should be asked earlier before we discuss about the time complexity. So we need to compare. First of all, we need to assess the performance of any algorithm. And when you have 2 algorithms, we need to compare which algorithm is better for the same problem, right? So to compare the performance of 2 algorithms and to predict the growth of runtime of any algorithm with change in the value of n. So as I said earlier, the behavior of the algorithm varies with the value of n, with the value of the inputs, with the change in the value of inputs. So asymptotic notations are will help us to compare the 2 algorithms as well as to predict the runtime of the algorithm with the change in the value of the inputs, number of inputs. Now consider 2 algorithms whose runtimes are say algorithm A1 and A2. The runtime of the first algorithm is C1n squared plus C2n, where C1 and C2 are constants. Similarly, the runtime of algorithm 2 is C3n. Just by looking at the runtimes, we will conclude that A2 will always perform better than A1, because the order of magnitude is just 1, n. But for the algorithm 1 it is n square. So we may say that A2 will always perform better than A1. But that's not the case if you look at the inputs. Now for the values, let us assume the values of constants C1, C2 and C3 as 1, 2 and 10 respectively. You could see that A1 is less than A2 for n is less than 98. You see the runtime of algorithm A1 is 99 until the value of n is equal to 9. This will go, here it looks like A1 performs better than A2 because the time complexity of A1 is 3 and A2 is 10 for n is equal to 1. So it goes. So this value, this remains same. So A1 is less than A2 for n is less than or equal to 98. Once n is greater than 98, then A2 will perform better than A1. So A1 is less than A2, so for n is less than or equal to 98, and A1 will be greater than, the time complexity of A1 will be greater than A2 for n greater than 98. So that is the unpredictable behavior. So here the value of n for which the behavior of these two algorithms changes, we call it as the break-even point of n. So in order to express this unpredictable behavior of any algorithm, we define the asymptotic notations. So we say that this algorithm will be better until the value of n is less than or equal to some value, or the performance of the algorithm will be equal to say 2n or 3n when the range of n, we specify the range, we specify the minimum range and the maximum range. So the asymptotic notations, the first one is big O, omega and theta. These are the three important asymptotic notations. The first notation, big O. The function f of n is equal to big O of g of n if and only if there exists positive constants c and n0 such that f of n is less than or equal to c star g of n for all n greater than or equal to n0. Here the c star g of n specifies the upper bound. So the time complexity of this of an algorithm will not exceed c star g of n for all n greater than or equal to n0. So we specify an upper bound for the algorithm. So that is big O. Big O notation specifies the upper bound for any algorithm. We state that the algorithm is always less than or equal to c star g of n for all n greater than or equal to n0. So in the big O notation, if the value of n is equal to 1, computing time is a constant. Big O of n, it will be linear. Big O of n square, if the time complexity is in the order of n square, it is quadratic, n cube, it is cubic, and then 2 power m will be exponential, and then log n logarithmic, and n log n. So these are the various types of big O notation. So remember, big O specifies the upper bound of any algorithm. It says that the algorithm will always be less than or equal to the upper bound. That is big O of n for all values of n greater than or equal to n0. The next notation is omega. Omega on the other hand is opposite to big O. It specifies the lower bound of any algorithm. So it is defined as the function f of n is equal to omega of g of n if and only if there exists positive constants c and n0 such that f of n is always greater than or equal to C star G of n for all n greater than or equal to n0. So here C star G of n specifies the lower bound for the algorithm. It is the minimum value. So always the time complexity of the algorithm will be greater than a particular value. So f of n is equal to omega of g of n. Omega of g of n specifies the lower bound. So always the algorithm, the time complexity of the given algorithm will be greater than or equal to C star G of n for all n greater than or equal to n0. So the function g of n is only a lower bound on f of n. So big O specifies the upper bound, omega specifies the lower bound. The third one specifies the range. It specifies theta. Theta specifies both the lower bound and the upper bound. So the function f of n is equal to theta of g of n if and only if there exist positive constants c1, c2 and n0 such that c1 star g of n is, so f of n is the time complexity of the given algorithm. We are specifying the minimum range and the maximum range. So c1 of g of n and then c2 of g of n for all n greater than or equal to n0. Hope you understand the three types of asymptotic notations. Big O specifies the upper bound, omega specifies the lower bound, theta specifies both the lower and upper bounds. So the time complexity of the algorithm will be between these two limits, between the lower bound and the upper bound. It will we are specifying both the lower as well as the upper bound. So f of n is greater than or equal to c1 star g of n, and it is less than or equal to c2 star g of n for all n greater than or equal to n0. So here f of n is equal to theta of g of n if and only if g of n is both upper and lower bound on f of n. So the same example, iterative sum. So you could see each step is an order of theta of n. So the time complexity of iterative sum will be given as theta of n. Both the upper bound and lower bound is a function of n, so it will be theta of n. Similarly for recursive sum, it will be like 1. If n is less than or equal to 0, it will be theta of 1. Otherwise, it will depend on the x. X is the time complexity of the recursive one. So it will be theta of 1 plus x. For matrix addition, you could see each statement. Statement 4 is theta of m. So the time complexity, the range will be both the lower as the upper bound is m. Similarly for statement, the next statement is theta of mn. So both the upper bound and the lower bound are m into n is m into n. So for the entire the time complexity of the entire algorithm is expressed as theta of mn. So it depends on the values of m and n. Hope you understood asymptotic notations. Why do we use asymptotic notations? As we are not able to express the time complexity precisely, and also the behavior of the algorithms is unpredictable, we just introduce asymptotic notations to define the asymptotic behavior of the algorithms. Thank you for now. Let us continue our discussion in the next class.